In this video, we're going to ask how do cells turn fatty acids into ATP? This builds off of my last video, sort of looking at fats as fuels in general. So if you haven't checked that out, you might want to go do so. But without further ado, let's tackle this topic. So how do we turn fatty acids into ATP? So let's orient ourselves quickly inside of the metabolic network. I've been using this transit network analogy across these videos. The network that we're in right now is the acetyl-CoA network. So everything's kind of centered on acetyl-CoA rather than on, say, glucose, like other parts of metabolism. That means we're going to be worrying a lot about here in the center, the citric acid cycle, this process inside of mitochondria that takes acetyl-CoA and converts it into carbon dioxide, reducing electron carriers along the way. The particular path we're going to be talking about today is this one here, this pink path, which is how do you take a fatty acid from, say, outside the cell and stick it all the way down in the citric acid cycle. This process is known as beta-oxidation, and what it does is it releases stored energy. Get rid of everything else here. It's releasing stored energy by taking these fatty acids, these long chains of carbons, and breaking them down into acetyl-CoA, which can then go into the citric acid cycle or into other metabolic fates. So let's just go through the steps. The first step is we're going to activate the fatty acid by attaching a coenzyme A molecule, a CoA. So we're going to take an ATP, a CoA, and our fatty acid. And we're going to generate a molecule known as acyl-CoA, adenosine monophosphate, and two inorganic phosphates. Now, the thing I want to note here is this CoA is the same CoA we've seen over and over. This is just like you see in acetyl-CoA, but now this CoA, instead of having just an acetyl hanging off of it, has an entire acyl chain hanging off it, hence the name acyl-CoA. The other thing you might notice is odd is we go from an ATP to an AMP and two PIs. We don't take this to, say, an ADP. And it turns out that energy is necessary because we're basically creating one of these high energy bonds that coenzyme A can use to donate groups to other places. And we would need more than one ATP to drive this process. So cleverly, what cells do here is they actually use one ATP but extract two ATP equivalents out of it. And the way that they do this is they have a single ATP molecule that is attacked by the fatty acid. That generates, that's over here. Come on, pen, there we go. That's over here. That generates this intermediate state, which has the adenosine and the phosphate. So this is basically the AMP, where the P is on this side, AM, attached to the fatty acid. So that's what this link looks like. And then that then attacks the CoA, yielding an AMP by itself and your acyl-CoA. The clever bit that gives the big energetic kick is that this kicked off two inorganic phosphates, right? We chopped the ATP into AMP and then this is called a pyrophosphate, the two phosphates put together. And it turns out there's a cell floating around, this pyrophosphatase, or cell, well, there's an enzyme that just floats around in cells called pyrophosphatase. It sees these and it just chops them into two inorganic phosphates. Breaking that bond is almost the same as breaking a normal bond, say, between an ATP and an ADP, breaking out that one inorganic phosphate. So effectively, we burned two ATPs to do this, right? We broke this bond and then we broke this bond sequentially. Cells use that two ATP equivalent to make this new high energy bond between the acyl and the coenzyme A. Okay, cool. Oh, the other thing I'll mention, I was going to say about this, sorry, is that this process is what I talked about in my last video when I said a fatty acid translocase, takes a fatty acid from the bloodstream and it goes into the cell and then it's captured by adding a CoA. This is that process. So this is how cells are importing and capturing fatty acids from the bloodstream. Okay. Once we've done that, we now need to transport our fatty acid to the mitochondrial matrix for breakdown. But we have a problem, and that problem is that acyl-CoA can't cross the inner mitochondrial membrane. I did a whole video about how hard it is sometimes to get things into mitochondria. This is one of those problem things to get across. Turns out mitochondria can't deal with CoA import. They just don't do it. So what are we going to do? Well, we're going to use a shuttle system. And in particular, the way we're going to do it is we're going to take this acyl group and we're going to transfer it onto this molecule here, which is an L-carnitine. That forms this acyl-carnitine here, where we basically transfer the acyl. I'm going to go back and forth a few times. We transfer that acyl onto that interior hydroxyl. The energy for this process actually comes from this high energy bond that we invested our ATPs into forming, right? So this is a thermodynamically favorable process. Oops, wrong way. Okay, so this is known as the carnitine shuttle. It's pretty nifty. So I'm going to walk through it at a process level. Maybe in a future video, I'll walk through this at a mechanistic level because actually it's pretty nifty too how all these enzymes do the job that I'm going to just describe here. But for now, just what's the process? So we have our acetyl-CoA. It's sitting in the intermembrane space, so in the cytosol. We have a carnitine that's floating around out there. That carnitine, it's sitting there. We have this enzyme, this carnitine palmitoyl transferase 1. This is actually sort of sitting on the outside of the intermembrane space. What it does is it catalyzes the reaction that I just showed you, taking the acyl group off of the CoA and sticking it onto the carnitine. This yields a free CoA molecule. The next step is to use this obligate antiporter named carnitine acylcarnitine translocase, often abbreviated as CACT. And what this enzyme does is it transports in one molecule of acylcarnitine, but during that transport process, it must transport a carnitine in the opposite direction. So this is a passive transporter in that it's not using ATP and it doesn't really have a directionality to it, but it does have the rule that you can't bring in an acylcarnitine unless you take a carnitine out. And that's going to be really important because that's going to make sure that for every carnitine molecule that goes in, even if it's bound to an acylcarnitine, it's still a carnitine backbone, right? So for every carnitine that goes in, a carnitine goes out. So the net flow of carnitine is 0. Okay. The final step in the shuttle is the carnitine, another enzyme is now going to take the acyl group off of the carnitine and stick it back onto a CoA. So it turns out mitochondria have their own pool of coenzyme A. And so all we're doing is we're taking that acyl group and we're sticking it onto a mitochondrial CoA in this point, generating an acyl-CoA in the process. This is a really cool process because actually if you walk through this, like I said, carnitine is net neutral, right? A carnitine molecule goes in, and then a carnitine molecule goes out. So overall, there's no carnitine moving across the bilayer. The CoAs, there's the same number of CoAs on both sides, so CoA didn't cross the bilayer. All that we did was we moved an acyl group from one side to the other. So if we put this in schematic form, basically what we're doing is we are taking an acyl-CoA in the IMS, we're dropping off that CoA, and we're taking a CoA in the matrix, and we're sticking the acyl onto that CoA in the matrix. So it's literally just a straight transfer of the acyl from the IMS into the matrix over the sort of slick carnitine shuttle move. Now, the reason this actually works energetically is because the acetyl-CoA is being consumed in the matrix. So the process of beta-oxidation, which we'll talk about here, is basically going to chop down that acyl-CoA into acetyl-CoA and then feed that into the citric acid cycle so that it's continuously being consumed. What that means is this is always generating more CoA. So let's walk through this whole process again. We have this acyl-CoA that comes in here, goes in as carnitine, comes out here as carnitine. That carnitine is being exported as part of the process. This is being consumed by the process. So let's start crossing out things that are being consumed. This is being consumed. This is being consumed. This is being generated. And this is being generated, right, by import. So what have we done? We've basically created a Le Chatelier's principle driver that's going to drive the system this way, right? We're going to basically suck acyl chains into the mitochondria by this process because just like we talked about, say, with the malate aspartate shuttle, we're running this favorable thermodynamic process inside. We're breaking down the acyl-CoA, in this case to make ATP. And as we're doing so, that is driving the import of the acyl carnitine. Okay, cool. So we made acyl-CoA in the cytoplasm, and now we've gotten acyl-CoA into the mitochondria by the mitochondrial shuttle. What do we do now? So now we're going to actually break this into acetyl-CoA by the process of beta-oxidation. So here I'm going to zoom up so we can look at it and orient ourselves for a second. This is an acyl chain, acyl-CoA, so we have our CoA here. And then what I've done is I've numbered the carbons, 1 through 16, starting left to right, and I've colored them in blocks of 2. So we've got a purple 2, a blue 2, a sort of teal 2, a green 2, etc., sort of in a rainbow array. And what we're going to do is track what happens to that molecule during the process of beta oxidation. So the first step of beta oxidation is going to cleave the bond between 1, 2, and 3, and 4, liberating an acetyl-CoA, right? That is now a standard acetyl-CoA. And now we have a 14-carbon acyl-CoA. Acyl-CoA, right? So we just chopped 2 carbons off, leaving behind an acyl-CoA rump. And so what this means is we actually had to have another coenzyme A come in to do so. It's a fairly cool and complicated process, but the way we can think about it is we're just dropping in a CoA that's breaking this acyl-CoA into now 2 parts. That continues. We now have the first acetyl-CoA that we generated, the second acetyl-CoA we generated, and then we have a 12-carbon acyl-CoA. And that keeps going. I would keep drawing it, but it would get boring. But hopefully what you can appreciate here is we are breaking this slowly but surely into a different acetyl-CoA. So we started out with a 16-carbon thing here. And at the end, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 acetyl-CoAs because we broke that into blocks of 2. And the process of beta oxidation is literally just this chopping into 2 carbon units over a sequence in time. You'll notice it is directional, that this isn't a willy-nilly, we're just chopping up the chain. Rather, we're chewing back from the activated CoA-attached side, slowly chewing back over the course of the beta oxidation reaction. Now, what are the yields of this? I already said that this yields 8 acetyl-CoAs because we broke it into that many pieces. What that actually gives us is 7 reactions because we had to break 7 blocks of 2 to get those 8 acetyl-CoAs shown here. 1, 2, let's get our pen. 1, 2, 3, 4, 5, 6, 7. And each one of those produces a QH2 and an NADH. So during beta oxidation, we're releasing a QH2 and an NADH every time we break one of these bonds. What that gives us then is a total yield of 8 acetyl-CoAs, 7 QH2s, and 7 NADHs. So a 16-carbon palmitate is going to give us this output. All right, so what does that term give us in terms of ATP? Because remember, this is happening inside of the mitochondrial matrix. What's going to happen to all of these reduced electron carriers is they're going to be oxidized, assuming there's enough oxygen around, they're going to be oxidized to their oxidized form with oxygen ultimately yielding ATP. So let's add up what the ATP yields are going to look like. So remember we had to spend 2 ATPs to prime the acyl-CoA. So we started out with -2. We're going to, through the process of beta oxidation, yield 7 NADHs, 7 QH2s, and 8 acetyl-CoAs. I showed that on the last slide. Those acetyl-CoAs can be fed into the citric acid cycle, right? This is happening inside of the mitochondrial matrix. And so that's going to yield 3 NADHs, 1 QH2, and 1 GTP per acetyl-CoA, right? That's every acetyl-CoA that goes into the citric acid cycle gives this yield. Which means if we add all those numbers up, you have 31 total NADHs, 15 QH2s, and 8 GTPs, and -2 ATPs. So this is sort of at the level of the individual electron carriers and triphosphates, this is what we've done. Let's turn those into ATPs, because remember, inside of the citric acid cycle and oxidative phosphorylation, you take an NADH and you can make it into ATP. The numbers are they depend a little bit on current physiological state and the like, but overall, it's about 2.5 ATPs per NADH, 1.5 ATPs for QH2. A GTP and an ATP are directly equivalent. In fact, you can turn one into the other. And obviously, an ATP is exactly equivalent to an ATP. So now let's take our 31 NADHs and multiply it by our 2.5 ATPs per NADH. That's going to give us 77.5 ATPs from the NADHs. Do that for everybody else, and what you get is a grand total of 106 ATPs. So breaking down one palmitate gave us 106 ATP molecule. That's the energetic equivalent. Seems like a lot. I don't know if you remember, but the glucose number is about 32. So a glucose gives us 32. Palmitate gives us 106, so we're getting more energy, at least in an absolute sense, from breaking down a palmitate than we did from breaking down a glucose. But how does this compare to other ways to generate ATP, right? Because there's different numbers of carbon, there's different issues at stake. So let's think about the different possibilities. So first, let's ask about it in terms of per gram. So if we divide by the molecular weight of the glucose or the fatty acid, we can ask how much ATP can we get per gram of the thing we burn? And so turns out that works out to 2 ATP. Since we get 2 ATP out of glycolysis and fermentation, so without oxygen, we get 0.01 ATPs per gram of stuff we burn. And that's 0.01 moles per gram. We get 0.18 moles of ATP per gram of glucose. And I really need to do this here. I'm totally in front of everything. Sorry. So if we're doing oxidative phosphorylation on glucose, we get 0.18 moles of ATP per gram. And if we do palmitate, we get 0.41 ATPs per moles of ATP per gram. So in other words, on a per mass basis, we're getting more than twice as much energy out of a fat than we are out of glucose. And we can put it this way, that we getting 2x the energy per gram compared to glucose. And this is actually a really big deal, right? There's a reason that we go to the energetic trouble to store things as fats, because it turns out we're mobile animals. We're moving around a lot. And well, do you really want to store everything as glucose and have to haul around twice your mass, basically? You can think about it. You can, if you took all of the fat that you have and you turned it all into glucose and kept the same energy amount, you'd have to carry double the weight that you'd have. So, I mean, I did some back of the envelope math. If your average person has about 30 pounds of fat on their body, now that's 60 pounds, right? Just if you stored it as glucose. So high energy density is really good if you're a creature that has to carry around fuel stores. Okay, so fat is great compared to glucose for energy storage. What about oxygen consumption? And so you can go through and you can ask for all the reduced electron carriers, how many ATPs do I get out per mole of oxygen that I put in? And that's what this ratio is here. The number of moles of oxygen that are required for each of these breakdown processes are 0 for glycolysis and fermentation, 5 for glucose and oxidative phosphorylation, and 23 for palmitate. If we then ask about how many ATPs per oxygen we get, turns out glycolysis is amazing at this rate. It doesn't take any oxygen, so you get an infinite amount per oxygen. You don't have to breathe to do glycolysis. You get 6.4 ATPs per oxygen out of glucose, and you only get 4.6 out of palmitate. So even though you're getting more ATP per gram of the stuff, it takes more oxygen per ATP that you get out. And so another way to put this is it takes more oxygen per ATP from fatty acids compared to glucose. You have to breathe more, basically, to break down fatty acids than you do for glucose. And this is great most of the time, but if you're, say, running fast for a very long time, you're not going to want to burn fats. You're going to much rather burn glucose. So high aerobic activities tend to be oxygen limited, tend to be glucose heavy rather than, say, fat heavy. Okay, finally, last thing I want to ask about is what about the speed of ATP generation? And answering this rigorously would take a lot more than I'm going to go into in this video. I'm just going to put it out there as like, what are the speeds? So glycolysis and fermentation are very fast. The first thing that happens if you take off running off of the starting line is you start doing glycolysis, so it's very fast. Glucose and oxidative phosphorylation is fast, and then fatty acid consumption is much slower. And you can just think about that in terms of all of the steps that have to happen, right? You have to like import the fat, and you have to do the carnitine shuttle, and you have to do beta-oxidation, and all these things. It's much slower than it is to get energy out of oxygen. So what that means is that in terms of ATP generation time, glycolysis beats aerobic glucose consumption, which beats aerobic fatty acid consumption. So, which also points to things like harder aerobic activities tend to prefer glucose, whereas less hard aerobic activities like going for a walk tend to prefer fatty acids. Okay, so let's summarize this, and then when we're done, what have we said? We said we break down fatty acids by this process of beta-oxidation, which sequentially cleaves these acyl chains into acetyl-CoA in the mitochondrial matrix. The output from this is that fatty acids have a very high energy density, but this high energy density is, the compromise for it is that access to it is slow and it takes a lot of oxygen to get to it. So there are definitely times you want to use fats, and there are definitely times you want to use sugars, and it turns out our physiology is quite tuned to do that correctly and efficiently. So Okay, so that's what I have on that. Hopefully it was helpful. I look forward to seeing you in future videos, and thanks for your time.